Hi everybody, my name is Alessio Trevisan. I am the Endurica product manager at Enginesoft. I work on offshore and construction department where I used to calculate special structures for that field of activity. During my career, I found elastomers on my path, and I can remember well that they could be a real challenge to an engineer that works usually with steel and aluminum like me, for example. So I'm very happy to introduce you Dr. Will Mars, that is a true expert of that field. A short presentation, if you still don't know Dr. Mars, he founded Endarica LLC in 2008 to give product developers a simple and accurate workflow for analyzing the durability of elastomer products. The firm's product and services are used by leading firms around the world to manage durability. And by the way, Dr. Mars has received several awards for his scientific contributions and innovations. He has more than 60 peer-reviewed publications, holds 4 patents in the area of elastomer durability, and is the past editor of 2 scientific journals. Today, in this webinar, he will explain us a very crucial topic that is testing and simulation for infinite life design. After his speech, there will be this possibility to make some questions. So without further hesitation, I give the floor to Mr. Will, Dr. Mars.
Thank you,
Hi,
Alessio. Yeah, thank you.
thank
Thanks,
you to you.
and thanks to Enginesoft for the opportunity to give this webinar. Um, it's a gonna kind of there's a when you talk about durability, there's just it's a huge topic space. And today's topic is going to be a little bit focused specifically on the aspects of fatigue that have to do with very long life. And So let's dive right in. Um, um, just a few words about Endurica. Um, so I'm the founder of the company. This is year number 17 for us. I started up in 2008. We did open an office in Luxembourg last year, so that's kind of new for us. And the entire history of the company, we've really been focused on elastomers and simulation and durability. Um, I just want to brag a little bit. Forgive me. But we just got word that if you're going to Tire Technology International, it's a conference in Germany, a couple weeks, we have been shortlisted for one of their awards. They haven't announced yet who's going to win, but we've been listed for R&D Breakthrough of the Year for a product that we're going to be a new capability we're going to be launching later this year for modeling oxidation in elastomers with a coupled structural thermal oxidative simulation. So if you're a tire person, check that out. All right, so let's. So this chart shows three major categories of fatigue analysis that the Endurica toolbox supports. Um, Infinite life, safe life, and damage tolerant. And you could think of these categories as being, um, let's say, organized in order from the very simplest level of analysis to more and more sophisticated levels of analysis. Um, the Endurica tools are have features that support all of these different workflows. Um, and just to define things a little bit, in the infinite life uh, workflow, what we're saying is that we want to sort of, just like metals, rubbers also have a fatigue limit, right? If you stay below the fatigue limit, cracks will not grow in fatigue. And so a simple way to design for long life is just to keep your loads below the fatigue limit. And that's what we call infinite life design. So when you do infinite life design, rather than trying to predict the life, all we do is we measure the fatigue threshold, and then we check to see how much margin do we have between our worst case load and the fatigue limit, right? So very simple analysis. It's sort of a go, no go, right? You either have it or you don't, infinite life. Um, if you if it is going to if you are below the threshold, you can calculate what's called a safety factor, which is simply the ratio S between your worst case load and the threshold. So if you say you have if you say that you have a safety factor of 2, that means that your worst case load is 1/2 of your fatigue threshold, right? Um, and now, of course, if your safety factor is less than 1, meaning your worst case load is bigger than your fatigue limit, um, at that point you'd be obligated to do the safe life analysis. And in safe life analysis, what you do is you say, um, um, your customer or a government regulation gives you a target life, right? 10 years, 100,000 miles, whatever. They give you a target life, and then the purpose of the analysis um, is to show uh, that the expected life um, is at least as big as the required life. So when we do this calculation, there's more that you need to measure about the material, right? You need a crack growth curve. Um, it's a deeper level of analysis. We're going to calculate in safe life analysis. We're actually calculating the number of cycles NF, number of repeats of a specific load case that it takes to get to end of life. Now, the limitation of safe life analysis is that what you do on one day a lot of times is not the same as what you do on the second day or the third day. And so in some cases, it's necessary to take into account the transient and the changing loads and material properties that are evolving with time, say. And in that case, we would use a damage tolerant approach. So anyhow, three levels of analysis. In today's webinar, we're really just going to focus only on the first category, the infinite life design category. We'll talk about safe life and damage tolerant another day, but today we're just going to focus on the infinite life analysis. So here's kind of an agenda for today's discussion. First of all, I want to just introduce a few principles that that we can use to understand and organize how we do characterization and analysis. So then after talking about the theory, I want to talk about how we do the materials characterization, right? How do you measure a fatigue threshold? And then once we do that, I want to talk about how you can use these principles in materials development, right? And people who make rubber parts a lot of times have a lot of choices about what materials and what sourcing they have for their materials. So we'll talk about how you can use these principles to select the right material for your application. And then finally, we'll talk about the simulation side, right? How do you use these ideas in the simulation workflow to get your design right? All right. So let's start with a few basics. When you're talking about durability in a rubber part, there's really 3 ingredients to that we need to think about. First of all, we have to think about crack precursors, right? If you get a microscope and look closely enough at your material, you're going to find that every rubber, even before it's ever experienced any load, always has some kind of microscopic feature that under load can grow as a crack. This could be undispersed carbon black or contamination of some kind. Like I say, microscopic, 10, 20, 50 microns in size. But that's one thing that's there. So from day one, you've got these crack starters, crack precursors in the material, and now and then the next thing we have to think about is crack drivers. So you've got these, small features, they concentrate stress. And then under the loads that you apply to your part, those small cracks begin to grow. And so we need to quantify the crack drivers. They're related to the stress strain behavior. We use a parameter called the tearing energy or the energy release rate, right? For those who may be familiar with fracture mechanics, it's kind of an idea from that field, the tearing energy. But obviously, bigger tearing energies lead to faster crack growth. Smaller tearing energies lead to slower crack growth. And so, we need to quantify what's the magnitude of the crack driving force. And then finally, the last thing that we worry about in general when we're thinking about durability is crack growth behavior. So typically what we might do is to make a plot of the rate of growth of a crack as a function of the energy input to the crack. And if you put enough energy in, the material will spontaneously grow cracks without any cyclic load, just in a single stroke. At lower tearing energies, you'll get fatigue crack growth. And then if the tearing energy is sufficiently small, then that's what we're talking about when we say a fatigue threshold, right? Is what's the minimum energy that it takes to grow a crack. So these are kind of the basic ingredients for any fatigue analysis. Here's an example of rubber's fatigue crack growth rate curve, and there's two or three features on here I want to point out. Like I say, if the energy input to the crack is sufficiently large, T sub C, that's the critical tearing energy, then at that point the crack is just going to grow spontaneously, right? So that would be a strength problem. As you back off on the energy, you're going to find that the crack growth rate slows down. And it's going to do that according to a power law that has a power law slope of F. And you can see this, if we're plotting on log scales, that's going to make a straight line relationship here in the mid-range. And then if I back off sufficiently, the parameter T naught, this is my fatigue threshold. Sometimes we also call this the intrinsic strength of the rubber, and you'll see why here in a minute. But that's really the parameter. When we talk about doing infinite life analysis or safety factor analysis, this is the parameter that we really are interested in, is the T naught parameter. So let's talk about the requirement. If you've got a sheet of rubber and it's got a crack, and if you imagine that crack is growing at some steady speed, you can ask the question, well, how much energy does it take to propagate the crack at some particular speed? And what we know is that if you want to grow a crack, then what that means is that every polymer chain, right? Rubber is a polymer, long chain molecules. But in order for a crack to grow, every single polymer chain that crosses the plane of the crack must break. And in order to break each individual chain, there is a required amount of energy, right? It's the bond breaking energy for these carbon-carbon bonds in the main polymer chain. And so, so if you so it's the energy to break a chain, and then it's also how many chains per unit cross section area, right? And the product of those two things gives you the tearing energy. Now, it turns out that's part of the energy that you need, but in order to get this polymer chain to load up to its breaking point, you have to stretch all the neighboring chains almost to break. And in the process of doing that, you're going to create viscoelastic dissipation. So in front of the crack tip, before the polymer chains break, there is this region here. This is an animation of an actual crack growth test. It's been imaged with an infrared camera, so you can visualize the temperature field in front of the crack. And what I want to point out is this red spot, right? There's this region in front of the crack where you have a large amount of heat generation, or that's mechanical energy being converted to heat. Um, and that's what we call the crack tip process zone. And of course, that takes energy as well. So if you imagine a crack growing at a constant rate, the energy required comes from two places. First of all, it's the chain breaking energy, but then it's also the energy that it takes to power up that crack process zone. And what we know about rubber is that um, the this chain breaking energy is actually independent of temperature and rate, and all the complexities that we normally think of with rubber. It's just a constant, right? It's like I say, related to what's the strength of the carbon bond and how many do you have per cross section. So it's, like I say, it doesn't depend much on temperature. Um, um, and but so the temperature and rate dependence of rubber's strength and fatigue properties really comes from the viscoelastic behavior in this crack tip. And you can see this TZ term. This is the part of the energy that comes that from that process zone. That is depending on strain rate, temperature, R ratio, and so on. Um, and I'll say that T naught for a typical rubber might be of the order of maybe 50 joule per meter squared. It's actually quite a small number. 50 joule per meter squared is not that much. Um, the and like I say, depending on how fast the crack is growing, TZ can be bigger or smaller. Um, if you're close to, if you're propagating the crack at a very high rate, TZ might be as high as like 100,000 joule per meter squared. Um, and then of course, as you back off, then that can be quite a bit smaller too. But um, all right. Now, yeah. So like I say, as a crack approaches a polymer chain, the polymer chain stretches out, and now in the measurements that I'm going to show you, we're going to use an experimental method that um, uh, uh, that uses a cutting with a blade to measure the intrinsic strength. That's kind of what you're seeing in this image here. We have a blade, it's penetrating into the rubber, and we load up the polymer chain and break it, and that's how we're measuring the intrinsic strength, right? So T naught is the intrinsic strength, and that's what we need to measure. And of course, if you're operating at energy below T naught, there is no crack growth. You'll hear people use different words: intrinsic strength, fatigue limit, fatigue threshold, threshold tear strength. Those all mean the same thing. All right. Now, so how do you measure this? Well, um, there's a couple different methods that you can use. The method that we use is a method that was originally proposed by Graham Lake and Eun-Hak Yeo, who at the time were working at the MRPRA in the UK. And they proposed a method that uses a very sharp blade. You use a planar tension test piece. You stretch the rubber, right? The blue arrows are showing the rubber stretching in the horizontal direction. And then once the rubber is stretched, you cut the rubber with a blade. This blade is instrumented. It has a load cell attached to it, so we can measure the energy input to the tip. The blade is meant to be as sharp as you can get it. Here's kind of a microscope image of the blade. Um, And so this is how the measurement works. And so to kind of talk a little bit more about how the measurement works is I showed before how the tearing energy, when the crack is growing at a certain rate, the tearing energy is the sum of two parts. You've got the intrinsic strength that I want to know, and then you've got this TZ part that represents all of the dissipative processes. Um, and if the crack is growing quickly, that's going to be a very large number that'll completely bury T naught. So in the experiment, what we want to do is find a way to get rid of TZ. And the reason that cutting with a blade works to do this is that uh, the order of the crack tip singularity when you have a blade is a higher order than if you don't have a blade, which means that the crack tip process zone is greatly reduced when you have a blade. And what you're looking at here is a finite element simulation that shows the size of the process zone as a function of the amount of stretch that you put on the rubber. So in the experiment, what we're going to do is we're going to stretch the rubber a little bit. We're going to cut it. We're going to stretch it a little more, cut it, stretch it, cut it. And we're going to look for the place where the input energy is minimized. And by doing that, then we can, make TZ as small as possible so that what's left is the T naught observation. Now you'll notice here I've got another equation to the right here that's got two terms. This is an equation that expresses the tearing energy in this experiment, and you'll notice there's two terms. The first term is the tearing energy that is in that the crack experiences. That's due to the opening of the crack, right? If I have a crack and I stretch the rubber, there's a certain tearing energy that's happening just because I'm opening the crack. That's without putting the blade on it. And then when I put the blade on, if I know the force on the blade, that's little f, then that contributes an additional uh, energy, and that's the second term here. So the first term is the opening component of the energy. The second term is the cutting component of the energy. Now, the measurements I'm going to show you are made using a device called an intrinsic strength analyzer. This is a machine that is sold by a company in Germany, Coesfeld. We actually worked closely with Coesfeld to bring this instrument to market, so that people would have a way to measure this. So it gives you results in about an hour or two that gives you T naught. It's a simple conservative test. And like I said, it avoids in the other method, you would have to do a fatigue test and reduce the crack growth rate sufficiently that you're approaching the threshold. The problem is that takes a long time. So this is a very fast and efficient test. And here's what it looks like to run the test. In this case, there's 4 strain levels. You can customize that. But here we've got 4 strain levels. So let's see. So this would be something like maybe, I don't know, 3%, 5%, 7%, 9% strain. You can customize that. But first we do a few cycles where we precondition the specimen. After the precondition, then we go to the first strain and hold. And then the second strain and hold, and then the third strain and hold, and then the fourth strain and hold. The hold period, if you look at this, it's something like about 10 minutes per step. Now, once we are holding at fixed strain, this third chart here is showing you the cutting force on the blade that's cutting the strip of rubber. And what I want you to notice is that for each of these hold periods, the there's kind of two let's say sub steps, right? So the first thing that once I hit my hold strain, the first thing that happens is that the machine will sort of stop and it will just let everything sit still for a couple of minutes, um, so that any viscoelastic uh, things can sort of die away. And so we call that the equilibration period, right? So everywhere you see a red rectangle, the machine is just sort of sitting still, everything's equilibrating. Um, Once everything's in equilibrium, then we begin to move the blade to cut the rubber. And we cut the rubber at three different rates. We have the first step is a very fast rate, right? So the bottom chart is the cutting rate as a function of time. So you can see in the first step, we start at a high rate, that's rate 1. Then we cut the rate by a factor of 100, that's rate 2. And then we cut the rate by a factor of 10, that's rate 3. So from the highest rate to the lowest rate, it's like a factor of 1,000 in cutting rate. And I'll explain why we do this here in a minute. But then for the second step, we repeat the procedure, and the third step and the fourth step, it's the same procedure. We start with a fast cutting rate, and then slow down by a factor of 100, and then slow down by a factor of 10. And that's the procedure that we're using to build up the data set that we need to measure T naught. So in fact, the reason that we're cutting at different rates is, the threshold is going to be the energy input at basically at the slowest possible rate, right? But since we can't really measure it at a rate of 0, what we do is we measure at a couple rates, and what we're hoping is that at the slow rates, that's close enough. And by measuring 3 rates, we're able to check and see how much dependence on rate the measurement has. If the measurement shows no rate dependence or very small rate dependence, then that tells us that we've succeeded in the measurement. If not, then we need to slow things down a little bit more. So here's some examples of the curves that come out of this measurement. What we do is from each of these, we take the final steady state cutting force value at each strain level and at each rate, and we plot them in these charts here. So what you're looking at here, this is a plot of the first term in the tearing energy equation versus the second term, right? So this is the opening energy on the x-axis, and this is the cutting energy on the y-axis. And you can see there's 3 curves here. The top curve is for the fast cutting rate. This was at 10 millimeters per minute. And then the next 2 curves are for the slower cutting rates. Factor of 100, factor of 10 smaller. And what's really beautiful here is that indeed these 2 curves are almost on top of each other, which indicates to us that this is a good measurement, that's close to giving us the threshold. So we plot these curves and we fit a line that has slope -1. Notice how this red line crosses the x-axis at 1033 joule per meter squared, and it crosses the y-axis at 1000 joule per meter squared. And these curves sort of are just kissing the red line. So the red line is what we would identify as what we call the threshold cutting strength. Now you'll notice 2 charts here, and the reason for that is that whenever we use this measurement can give you a relative indication of the fatigue threshold. It's not an absolute measurement. So normally what we do is we'll run the experiment on a known control material that has a known fatigue threshold, and then we'll run it on the material that you want to use actually in your application, the feature material, and then we'll compare them. And that lets us calibrate for an absolute threshold value. So for example, in this case, this is a material that was provided to us for a grommet application. You know, the story for this one was that when you use a grommet in a vibration application, the amplitude of the vibrations can be quite small, which means you have a very large number of cycles, but you still want to know that you've got, you know, you're not going to have fatigue problems. So if we just measure the fatigue limit, we can make sure that for the grommet we stay below the fatigue limit. Now, in this case, for the control material, we know that the fatigue limit was 47 joule or 48 joule per meter squared. And we measure the cutting energy as 1162. For the grommet material, we measure a cutting energy of 1033. And so the fatigue threshold that we would measure or report then would be basically 47.7 times the ratio of 1033 divided by 1162. That's going to give us the fatigue threshold for the grommet material. And you can see here, this is a plot comparing the cutting energy that we measure with the blade to the inferred fatigue threshold. You'll notice they are different numbers. The reason for that is that the blade is not infinitely sharp, right? There's a a finite radius of curvature at the blade tip, and so the difference between these reflects the sharpness of the blade. And so when we run this experiment, we need to we run the control material so we can calibrate the for the sharpness of the blade. This was an experimental validation that Lake and Yo published for 6 different rubber compounds. And this was the paper where they showed that, yeah, if you measure this cutting energy, it's very nicely correlated to the fatigue threshold that you would measure using very, very long crack growth tests. For our study, we end up with a fatigue threshold of about 42 joule per meter squared for the grommet compound. And this is my plot of, you know, what we measure for cutting energy versus what the fatigue threshold is. Now I mentioned that there's other methods for measuring fatigue threshold. The most obvious method is to actually just do crack growth tests. And so on the left here, you can see this is for a control material that we use. This is for the control material that we use in our work. It's an EPDM compound. What I want to show you here is that if you're going to use the direct method for measuring threshold, the crack growth tests that you have to run are crazy long. Like in this case, we're able to measure the upper end of the crack growth curve in about a week, right? That gets us down to about 10 to the minus 7 millimeters per cycle, but you can't really see a threshold until you get down to about 10 to the minus 8 or 10 to the minus 9. And so just this last little bit of data on the curve takes about 8 months if you're going to try and use the direct method. So so much more efficient, obviously, to run a 1 or 2 hour test than an 8-month long test. And we did, if there's a paper I'm citing here, this is a paper where we actually went back and we ran both methods on the same material, and we were able to show that we ended up with measurements that were quite similar. So using the direct method, we measured, in this case, 47.7 joule per meter squared. Using the ISA cutting method, we got a value of about 48.6. All right, so that's kind of a little bit about the theory and the test method. Let's talk about how we can use this information in materials development applications. So a lot of times in materials development, the question that you're faced with is which material is the one that's right for my application. And so, it's kind of A versus B, and how do you rank things and so forth. One of the tricky things in fatigue when you're ranking compounds is that the ranking can depend on the severity of the load in your application. So what you're looking at here is a crack growth chart for two materials. The green data points are for natural rubber, and the orange data points are for a butadiene rubber. And you can see they're quite different. The butadiene rubber is a much weaker material. Like if you do a tear strength test, the butadiene is going to break first at a much lower load than the natural rubber. And you can see that as higher rates of crack growth here compared to the natural rubber. But if you keep reducing the energy input sufficiently, right, as you approach the threshold, there's a reversal. And so, in fact, at very low loads, it's actually the case that the butadiene rubber has a higher fatigue threshold than the natural rubber. And so if you have an application that is operating at low load and never sees larger loads, you might actually choose the butadiene rubber because it's going to give you a bigger fatigue limit. So like I say, you need to be a little bit careful to evaluate when you're choosing materials. You need to take into account how much load you're putting on the material. So now the data set I'm showing you here is from a full-blown crack growth test that we run on a servo hydraulic machine. In this case, this was run with the tear and fatigue analyzer from Coesfeld. This test takes about 20 hours to collect this data set. Now, again, when you're a materials person, a lot of times you want to screen large numbers of candidate materials, and if your test takes a whole day, that's inconvenient. So one of the really nice things about this intrinsic strength type of test is, again, it executes rather quickly. And in this test, you measure the fatigue limit. This test can also give you TC, the tear strength for the rubber, right? After we do the cutting test, then we pull the blade out, and then we just do a pull to failure on the specimen, and so that can give us TC as well. One thing I want to point out is that T naught and TC, you can think of them as upper and lower bounds on these fatigue crack growth rate curves. And so as you change materials, the value of TC might change. You can imagine that the intermediate behavior is going to change similarly. And we can use that principle to make rapid estimates of the crack growth rate behavior. So what I'm doing here is I'm overlaying in this slide the results of the 20-hour crack growth test, right? The triangle data points here and the square data points here. That's the 20-hour crack growth test, and you can see you get a certain power law slope. And what I'm going to do then is take the measured T naught and TC values for these two materials, and for T naught, I'm going to plot those at a crack growth rate of 10 to the minus 8 millimeters per cycle, right? So you can see here T naught for the natural is about 50 joule per meter squared. For the BR, it's about 100 joule per meter squared. So you have these. And then if I plot the TC value at a crack growth rate at 0.01 millimeter per cycle, then you get this reversal in ranking. And if you just draw a line connecting these 2 points, you can see that it actually reasonably approximates the crack growth rate curve for these two materials. So it's not exactly precise. The slope that you would get with this simpler method isn't exactly the same as what you get with the actual crack growth test, but it's in the ballpark. Which, when you're sorting material selection options and you've got a lot of them, this can be a very efficient way to rank order your materials. So yeah, like I say, the key to this rule of thumb is just to remember that 10 to the minus 8, 10 to the minus 2, those are just kind of a rule of thumb guess here. In actuality, they might be different numbers, but for purposes of estimating in a materials selection context, you can use this as a. In fact, I call this the Robertson rule. For anybody who may know Chris Robertson, he kind of originally noticed this trend in our data sets. And so anyhow, so I call this the Robertson rule. And here's an example of the calculation, right? So if you give me TC and T naught, I can just use this equation right here, F equals log RC over R naught, which in this case is going to be, 10 to the minus 8 divided by 10 to the minus 2 divided by log TC over T naught. And that gives you an estimate of your power law slope. And so you can see here for the NR, the actual experiment gives us 1.95. Our approximate method gives us 2.3. For the BR, we see 5.2. And for the approximate method, we see about 3.9, or so about 4.0. And we've actually tested this out on a large data set. We've gone back to, a database of materials that we've measured, both T naught and the crack growth curve, and we compared the actual slope values with the F values that we calculate using this simple method. And it's not perfect. You can see there's a bit of scatter here, but the correlation is something like R squared equals 0.8. Which for again for purposes of doing materials development is probably good enough. All right, so just to drive home the point that if you're going to use just T naught and TC without doing a crack growth test, it's a bit like it's a bit like using a thumbnail image, right? This is a very low resolution image. You wouldn't scale this up and present it to people as a pretty picture, but for getting an idea of what things look like, it's a very useful tool. All right. So anyhow, so that's Robertson rule, is just if you measure T naught and TC, you can sort of fake in these crack growth curves, and you can do this to do a very rapid low time, low cost sorting of your material options. Okay, so last topic, let's talk about using the fatigue threshold T naught in a simulation. So this is the workflow where we're going to calculate a safety factor, right? The safety factor is the ratio between your fatigue limit and your worst case load. And so typically this might look like this. Obviously you're gonna measure your rubber stress strain response. You're gonna do some kind of nonlinear analysis of your duty cycle. You're gonna have experimental measurements of your precursor size, and experimental measurement of your T naught value, using maybe the ISA. And those are going to all go into your analysis. The safety factor is an output that you can request from the Endurica CL fatigue solver. So you just put in your strain history, put in your material properties, and what you get out is one thing you can get out is safety factor. When you use the safety factor analysis in Endurica, it is going to, in cases where you have multi-axial loading, it's going to use a procedure called critical plane analysis. And the purpose of critical plane analysis, like I say, is to take account of the multi-axiality of loading. What we do is we say that every point in your part has cracks that are oriented in all possible orientations. So we actually calculate the safety factor for all of the possible orientations that a crack might have. You can see in this animation, this red disc is a representation of the crack, and we're basically calculating a value of S for each orientation that the crack might have at a given point in your part. And what you're going to get then is basically, if you sort of if you follow the unit vector to the surface of the sphere and then color each point, you'll get a colored ball where you see red, that's the place where the safety factor is the smallest. Where you see blue, that's where the safety factor is the biggest. And what we report for each finite element is the value of the reddest point, or the smallest safety factor. So that's so this not only gives you the safety factor, it also gives you the orientation of the plane for each element that is the closest to being, not infinite life. So let's apply this to our grommet. Here are some material properties for the particular rubber that we've got. You can see I've got a stiffness of shear stiffness of 3 megapascals, a precursor size of 100 microns, and a threshold of about 800 joule per meter squared. And I've got 3 load cases: a high, a medium, and a low load case that I want to model. And maybe I'm developing some specs for what the allowable loads are for this grommet. So here's the grommet running under the low load condition. You can see that here I've colored the cross section of the grommet based on the safety factor. The color scale is set up so that a value of safety factor 1 is red, and anything with a bigger safety factor is a cooler color, right? So blue is a very large safety factor. Red is a safety factor of 1. And if you see any black in the plot, then that means that the safety factor is less than 1, which means that in those locations you would not expect to have infinite life. Now, for the low load case, the worst case safety factor in this simulation was about 2.6. So this grommet would be qualified for the low load for infinite service under the low load case. And the sphere here that I'm showing is specifically the safety factor distribution for the element that has the lowest safety factor, 2.6, right? So this shows you the orientation of the crack that gets the worst load case. Now, if I repeat the analysis for the medium load case, you'll notice just this tiny little black spot on the tension side of the grommet load case. And if you look at the value of safety factor there, I'm reading S equals 0.8. So this is an indication that I would not expect infinite life here. The life may still be acceptable, but this is a case where maybe you would do a deeper analysis and look at the safe life approach to calculate well, how many cycles does it last? But it's not going to live forever. There is a potential here for a crack. And then obviously for the high load case, you can see it's an even worse situation. Again, you'd probably want to do the safe life analysis. So in this case, the grommet qualifies for the low load, but it doesn't qualify for the medium or the high. And so very simple analysis. This is a good example. Here's another example of where you might use the safe life analysis. In this case, this is for a tire rolling under steady state. And what you can see is that in this case, I've colored the elements in the cross section of the tire. It's a 3D tire model, but we've basically followed each streamline around the tire and computed a safety factor for each streamline. And then we've just colored those on the cross section of the tire. So you can see the smallest safety factor in the tire is near the tire's belt edge. In this case, for these conditions, we have a safety factor of 4. So this would tell you that this tire under these conditions, could be expected to to not develop cracks. And a final example is this fertilizer squeeze pump. So these are basically hoses, rubber hoses, that pump the fertilizer out of these tanks and onto the field. And the way this works is there's some rollers that squeeze the hoses and force the fluid to flow through the hose. You can see here's a simulation of the rollers squeezing the hose, each of the 6 hoses. And here, this is just taking one of the hoses and taking a cross section and then looking at the safety factor on the hose cross section. You can see we're getting a safety factor of about 6. So for this application, under this amount of squeeze, we would predict indefinite life. But again, the beauty of this characterization is it's very simple. It's just a single test to get me my threshold value. When I use the infinite life method, I don't need to worry about rate or temperature dependencies. All of that we would worry about that in a safe life analysis, but for these infinite life analyses, we just need to make sure we're below T naught, which itself does not depend on temperature or rate. All right, so I'll just summarize here and say that if you want to characterize this, you want to use the intrinsic strength test. It's a great screening test. If you're looking at long-term durability, it gives you the threshold T naught that if you run it with the control material that you can use to plug into your simulations and get safety factor. And if you want, you can use the Robertson's rule to get to quickly estimate a crack growth curve. The analysis that we've showed you is great for understanding basic failure mechanics without getting lost in all of the rubber's special material behavior, and it can give you a safety factor, which is good for doing A versus B maybe in design. It's using the full power of critical plane. So if you have multi-axial loading, it's a very accurate way to and conservative way to look at that, because you're looking at all the different ways that a crack could grow. The only limitations on this is obviously it doesn't consider aging. So we say infinite life, but in fact, if the rubber ages, the material properties can change. The value of T naught itself can change with like if you have a heat exposure, T naught, the value of T naught can change. And so, you want to be careful about that when you're doing this analysis to make sure that you're covering your bases with respect to aging. Obviously, when you use infinite life, you don't get a fatigue life. If you want that, then you're gonna have to do the safe life or the damage tolerant approach. So that really covers the topic, and I'd be happy to entertain if there are questions or comments. I would say I think you can type those into the chat, and we can certainly talk about those if there's interest.
Yes, it is a good choice to write down on the chat, or also take notice of contacts in which we provide an answer. But if you have some question, this is a good occasion to have Will reply to you directly.
Yeah, and I'll just mention that while people are thinking about what they might ask, I'll just mention that we've got 2 classes coming up in March. The first class is going to be our testing class, where we will where we'll talk about the experimental methods. That's March 17th. And then we have our simulation class, where we're going to talk about the software on the 25th. So I'll just mention that really quick. But
it's a great news. You have also one question on the chat. Can you use that approach to plastics?
That is a really good question. And the answer is I don't know. Plastics tend to be quite a bit harder, and the inelastic behavior in a plastic can be much stronger than in a rubber. So I would sort of expect that the process zone in front of a crack for rubber for a plastic is probably going to be harder to suppress with cutting. I know that on the Coesfeld instrument, there's a limit on the load cell for the blade. So if you were going to do this with plastic, you'd probably need to work with a very thin sheet, or you'd have to probably beef up the load cell. But I'm not aware that plastics people have used this method. Like I say, this method's been around for a while in the rubber world, but I'm not aware that plastics people have picked up this method. I do expect that plastics have a fatigue threshold, and that you could do the safety factor analysis. It's just a question of how would you measure fatigue threshold for a plastic.
So, thank you, Will. We have another one question, and it is possible to use Endurica to predict the life of bushings under vibration loadings?
Yeah, thank you. That's a great question. So um, for sure. So probably if you want to predict life, then you're going to need to use either safe life or damage tolerant. Um, but yes, you can simulate those vibrations um, with ANSYS, and we have a tool that we haven't mentioned here called EIE that you can look at random vibrations um, and um, and uh, and so yeah, that's definitely a tool that you can use to look at bushings and vibrations. All
Okay, we
right.
need to. Okay, time flies. So the way we have to close this webinar since there is also other webinar scheduled. And if you want to make some other question, please refer to me or uh, uh, to Will. On the fly, we have a comment of Alexandre Moisier, and basically it says that white analytical line reduce the difference between the actual values of experiments. I think we can reply
I
via.
d
Yeah, yeah,
but
yeah,
I can reply. So I can send an answer. I'll comment on that, and NGINSoft will send out an email. I think as a follow up. I think this has been recorded, if I understand right. Is that right,
yeah, yeah,
Alessio?
yeah, 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 yeah. It's
Yeah.
right. The webinar will be recorded and will be available on our website. We'll share. So I think it is so. So no problem about that. With the question, yes, we can provide to forward a reply, a complete reply via email.
All right.
So feel free to contact us with many other questions and we will reply.
All right. Thank you.
Okay. Thank you, everybody. Thank you for attending this webinar. And obviously, thank you, Will, for your always interesting speech. And see you next time.
Ciao.
Grazie. Ciao. Bye bye.